Hi, thanks for coming. As this says, this is not my work, this is Eric's work. So I'm going to be kind of phoning this talk in, so it's a joke. But I should warn you that, so I'm confident that I can communicate the general ideas here, but if some of the technical details, I'll have to refer you to him on. Okay, so this is about sizing smart trials for the estimation of high-quality treatment regimes. Okay, and these are some of the folks who have contributed to this. Eric Rose is the lead author on this work. He's one of my colleagues in the lab. He's a grad student of Eric's. Okay, so I don't have to sell you guys on precision medicine, but we're going to be talking about treatment regimes in particular, which are one way of personalizing clinical decision making. So we're going to run a sequential clinical trial where we give patients a sequence of treatments, and then we're going to try to estimate the best treatments to give them given their personal information at a particular time. Okay, so what do I mean by a decision rule, a treatment regime? So a treatment regime consists of a sequence of decision rules. In this talk, we're going to be thinking about two-stage regimes, so we're going to have two decision rules. So this is a decision rule that was estimated or constructed from data from a study on PTSD in cancer patients. So a patient comes with some baseline characteristics, so they have some distress score, PTSD symptoms. If these are high, then we recommend that they see a cancer distress coach, and otherwise they get the usual care. And the second stage decision rule will be based on more information that is gathered at some intermediate time. So we're personalizing care for these patients, and we want to figure out how to do that in the best way. All right, so this was the study that this rule was estimated from. So we randomized patients to treatments at each stage, and then once we have all the data, we can try to estimate the optimal adaptive rule. Okay, so how are, and I'm going to be, this is going to be talking about SMART trials, sequential multiple assignment randomized trials in particular, which are just trials with this structure. We randomize to one treatment and then randomize to the second stage, among the second stage treatments. And then observe some outcome of interest. Sorry if I rushed through that for those of you who aren't familiar, but we've already seen some talks on SMARTs the past couple of weeks. Okay, so sample size calculations for these sorts of trials are typically done as follows. You power for simple comparisons of means. So, for instance, if I have binary treatments at each stage, I might compare the sequence 0, 1 to 1, 0. And that doesn't pose any problems as far as inference or power calculations are concerned. We can just use nice old t-tests for that. And then if I want to estimate an optimal treatment regime from the data resulting from the SMART trial, I do that as a secondary matter. In the inference, as we'll see for this statistical problem, the estimation of the optimal regime is difficult, which may be one reason why this powering for this reason is not widely done, or maybe done at all. I'm not. Yeah. Okay, so the standard approach goes like this. As I said, we power We power the SMART for some primary analysis of comparison of two fixed treatment sequences, say. We estimate an optimal regime and evaluate it perhaps using cross-validation. And then we still want to know something about the value of this optimal regime. So then we run a follow-up study comparing the estimated adaptive decision rule to some control. And this also can be done using standard inference and power calculations. So this doesn't pose any technical difficulties. However, running two trials is presumably more costly than running one. And you also have delayed clinical impact because you roll out the learned improved decision rule if you find one later. Oops. And you haven't designed either of these studies to ensure that the learned treatment rule is of high quality, right? Because so you didn't power this study. You didn't power this study to make sure this thing was of high quality, and then you're comparing it to some control, right? But you could have compared something much better to the control had you powered the original study for the estimation of a high quality regime. By high quality, I mean one that gives you patients better high outcomes when followed in expectation. Okay, so if we could, the best thing to do would be to run a single trial that allows both for these primary hypothesis tests and for the estimation and evaluation of the optimal regime. Okay, so some folks don't like this because it has associations with subgroup identification, and it's widely held that sizing for the purposes of estimating a high-quality regime would require a prohibitively large number of subjects. It wouldn't be possible to guarantee frequentist operating characteristics, and the theory couldn't even get off the ground without making strong assumptions about the generative model. So what this work is aimed at doing is showing that these fears are not necessarily well-founded. It will turn out that we can come up with sample sizes that are not prohibitively large, that give frequentist guarantees on the estimators, and that we can do it without making strong assumptions on the generative model. So that's the goal of this work, and in particular, there are two approaches for calculating sample sizes. One does make strong distributional assumptions on the generative model, and I say main focus, but I think we'll probably divide our time roughly evenly between these two. Not sure, but this will make the inference relatively easy when we make certain assumptions, but we also can get away with much weaker assumptions and still get sample size calculations, with the caveat that this procedure requires access to a small data from a small pilot study. Okay, and then the philosophy is that having demonstrated that we can do sample size calculations based on these two extremes, we can then adapt to cases where maybe we don't want to make such strong assumptions as in the first case, but still don't want to go to the fully non-parametric approach that is presented here. All right, so the next part I will be talking about, I'll be giving the setup and notation for the data that we have and how we are going to be estimating the optimal regime. So as I said, we have a two-stage trial. We measure some baseline information before doing anything, and that's x1. Then we take our first action, or our first treatment, A1, which will be binary. We observe interim information. We make interim measurements on each patient or each subject after the first treatment. Give the second treatment, which is also binary, and then we observe the outcome of interest, and that's what we want to optimize. And we're going to call the histories everything that we know at times 1 and 2 respectively. So everything we know at time 1 is just the baseline covariates, and everything we know at time 2 is the baseline covariates, the treatment that was given at time 1, and the intermediate covariates, interim covariates. And we are going to be talking about the value or estimating regimes, which are sequences of rules mapping these histories to treatment decisions. Okay, so how do we characterize the best regime? It's the one that maximizes the expected value of y when followed. And we can actually write down the optimal regime via these things called the Q functions. And this may be reviewed for some of you. So Q2 is the conditional expectation of the outcome given the subject's history at stage 2 and the treatment they were given at stage 2. So that's straightforward. Q1 qualitatively says, given what I know about the subject at time 1 and the treatment that I give them at time 1, and that I plan to take the optimal action at the second stage, how well do I expect to do? So that's what this max is doing. And if we take at each stage the argmax of these Q functions given the respective histories of those times, we will have the optimal policy. Or I may say policy sometimes. I mean, it means the same thing as decision rule or treatment regime. So there are many ways to estimate the optimal regime. The sample size procedures presented here will be assuming that the analysis is done with Q-learning, or that the estimation is done with Q-learning, which mimics this sequence of conditional expectations that we don't know with a sequence of regressions. So we're going to postulate a linear model for the Q function, for each Q function. We're going to first regress the outcome, the observed outcomes on the observed histories and treatments to get an estimator of Q2. Then we plug in the optimal action, the optimizer of the estimated Q2 to create a so-called pseudo outcome, which will be the target of the next regression, and regress that on the observed stage 1 histories and treatments to get an estimator of Q1. And then our estimated optimal policy is just the argmaxes of these estimated Q functions. And we emphasize the dependence of this estimator on n, because of course we want to pick the sample size n that ensures certain characteristics of this estimator, which are as follows. Qualitatively, we want to power the study to satisfy two criteria. One, we want to size the study so that it has satisfies these two criteria. One, we want there to be a certain power against the hypothesis that the optimal regime provides no improvement over some baseline beta naught, which corresponds to like the standard of care. So eta here is some clinically meaningful improvement in the average patient outcome, and we want to test the hypothesis that we want to power for the hypothesis test that the value of the optimal regime exceeds the the standard of care value. Okay, so that's PWR for power, and then opt for optimal. We also want to ensure that the value of the estimated regime because that's what we're actually going to be following, is close to the value of the optimal regime, where we get to choose how close we want, that's epsilon, and the probability of being within epsilon of the value of the optimal regime. Okay, so this is these two criteria are what are going to be satisfied by the two sample size calculations that I present. All right, so I told you that the first approach was to make a lot of parametric assumptions on the generative model. So this set of assumptions is something like normal linear model in the case of just regression. So this is in some sense like the simplest and nicest parametric distributional assumptions we can have on the Q function in the generative model. Roughly speaking, it says that the stage 2 Q function is correctly specified as a linear model. And then it tells us something about the linearity of the stage 2 histories in the stage 1 histories, and that these are normally distributed. And this normal error, it doesn't actually have to be normal, but an error with a density that's bounded away from 0 is technically what's going to make the inference for this be really nice. So as some of you may know, what screws up everything in Q-learning is this max operator, which makes this problem in general non-regular. But if we make these assumptions, and in particular, if we make this sort of smooth distributional assumption on these features, then we get around that issue. So that's what this is for. And then these are normally distributed, the stage 1 histories with these. Okay, so the upshot of this, I'm not going to walk through the details of the formula, but the upshot of this slide is that we can write the value of the optimal policy as a smooth functional degenerative model, as a smooth function of these parameters that I showed you on the previous slide. And that's what's going to make inference for this relatively nice. So we can obtain, given a plug-in estimator of the value of the optimal policy, which is obtained by estimating these parameters and plugging them in, we get the asymptotic normality of that estimator where its limiting variance is a smooth functional degenerative model, which in turn will allow us to get a nice power calculation that looks quite familiar. So this is 1 minus gamma is the, let me make sure I've got this right. So let's remind ourselves what all these Greek letters are. So we want to power at 1 minus gamma, and eta is the minimal meaningful effect, and our test is of level alpha. So we, based on the asymptotic normality of this plug-in estimator of the value, we get this familiar sample size calculation for formula for the sample size. So that's it for power, assuming we have a consistent estimator of this variance, which, as is often done, can be elicited from experts, estimated from pilot data, and they also in the paper, just as kind of a remark, give an argument for how a conservative estimate of this variance can be obtained from the observed data itself, in particular from the observed outcomes. Okay, so that's the power criterion. Now for the quality of the estimated regime. So we have this bound on the difference between the value of the estimated regime, the value of the optimal regime, which is again what we want to bound, and it's bounded in terms of this thing that I just told you on the previous slide. We know how to control, right? So this is and plus some term that will be negligible when we scale by root n. So this leads from this formula and the asymptotic normality of this thing to a sample size calculation for the second criterion, where this is the this is epsilon is how close you want the value of your estimator to be to the value of the optimum, and 1 minus zeta is the probability that it's within epsilon. Okay, so that is it for the high structure, the strong assumption version of the sample size calculations. Yeah. 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 Uh-huh. Is the major term, so we scale by root n, which makes this asymptotically normal with a fixed variance, and then this is negligible. So what's the question? Okay. Okay, so the second approach, remember, one of the worries about sample size calculations for estimating or for powering studies to ensure the quality of the estimated optimal regime, one of the worries was that we couldn't do it without imposing a lot of parametric structure, which is what we just did. So can we do it without imposing all that structure? The answer is yes. But it's a more difficult problem because in general, there are not regular or asymptotically unbiased estimators of those Q functions because of the regularity issues that the non-smoothness that's introduced by that max operator in the algorithm. Normal approximations are known to perform poorly in finite samples, and there's no closed form for the power of the relevant hypothesis tests. But we can still get a conservative, valid hypothesis test by constructing a projection interval, and I'll tell you how that is constructed. And then I told you that we would need access to data from a pilot study. So the reason we need to do that, we need that is that we will bootstrap over sample from those data up to proposals for the sample size of the trial we're sizing for, and compute the power at each of those proposals to solve for the size that we want. And we have to do that because there's not a closed form for power. And yeah, so that's our way of dealing with the news. Okay. All right, again, with Q-learning, we're still going to assume, we're still going to do Q-learning with linear models, but we're not going to assume that these models are correctly specified. But we are still free to talk about what I'm going to call pi-Q-opt, which are the population parameter the population is the population analog of the pi that is obtained from the Q-learning algorithm, regardless of whether that is correctly specified. And then we're going to be fulfilling the criteria where the comparison is with the value of this this policy, which is the sort of the best that we can do if we're committed to using the Q-learning algorithm for estimating the policy. Okay, so I don't think there's anything new here. All right, so we just make assumptions about moment and tail conditions. I said that inference is difficult and we'll have to base sample size on conservative interval estimators. Okay, so this slide just tells us how we're going to estimate the value of the policy corresponding to the estimated Q function. So for parameters beta of the Q function, for fixed parameters beta, we're going to define delta of beta just to be this augmented inverse probability weighted estimator of the value of the corresponding policy. So that is an unbiased estimator of the actual value and still consistent for the value of pi q opt, even if the Q function is misspecified. All right, and the reason we wrote it this way is so I can explain what the projection interval is easily. The projection interval works as follows. We can't get a nice interval for beta, the first stage Q function parameters. These guys. This is what is non-regular because of this max. However, if we knew the second stage parameters, then we could do inference for this fine. If you just handed me a beta and you said this is the actual beta, we could do inference for this fine. Right. And then on the other hand, how does this work? One sec. So right. So then if we have a value, on the other hand, if we have an estimate of the value of beta, for a fixed beta, that's also asymptotically normal and fine. So the idea is to first construct a confidence interval for beta star 2, which is the population analog of beta hat 2, which we can do fine. And then for each element of that confidence interval, construct a confidence interval for the value of the corresponding policy. And then we take a union over all of those confidence intervals to get a conservative confidence interval for the value. So that is how the projection interval works. And from an interval constructed this way, we can get a conservative but valid hypothesis test for the hypothesis of interest. Okay, and this is exactly the power of that hypothesis test. It's just that there's not a closed form, so we need some way of computing. We need some algorithm for computing this. And the way the way we do this is we have a pilot study of size n naught, and then we bootstrap sample up to proposals for n. And we just solve for, we bootstrap oversample from that smaller data set up to samples of size n and solve for n where we have the requisite power for this test. for the given eta, for the given effect size of interest. Okay. All right, so this is just saying what I just said. Okay, and then this theorem is really ugly, but what this is basically saying is the power curve that we obtain, the estimated power curve from this bootstrap sampling, oversampling procedure is consistent for the actual power curve of the test as n naught and n diverge. And Eric tells me that this limit can be taken with in any which way. So while the most realistic asymptotic regime is where n naught is going to infinity slower than n, because our pilot study is going to be significantly smaller, presumably, than the study that we're powering for. But this does not depend on the details of how that limit is taken. Yeah, so this is just the consistency of the estimated power curve under this bootstrap oversampling procedure. Okay, so that is it for the satisfying C1 and the C2 are supposed to be PWR and opt. So we do an analogous procedure for ensuring that our sample size is big enough that the value of the estimated optimal regime is close to that of the true optimal regime, by which I mean pi q opt, not the globally optimal regime. And we didn't assume much of anything about the generative model or that our Q functions were correctly specified. But it is harder to compute this, and the theory is difficult, and we do have to have access to some pilot data. But those are the two sample size calculation procedures. All right, so the generative model focuses on non-standard cases, meaning cases where the effect size is small. Which are the cases that cause trouble for inference. We have normal errors and correctly and incorrectly specified Q functions. Actually, in the incorrectly specified Q functions will be part of the misspecification comes in non-normal errors in the stage 1, in the stage 2 histories. So the stage 2 covariates. So we, one hypothesis tests at level alpha. The desired power is 90. The epsilon they choose for deciding what counts as being near optimal is 0.3. And the probability of being within epsilon they want to ensure is 0.9. And we select the sample size so that both of our criteria are satisfied. And then they also compare the sample size that you would get for just comparing two fixed regimes. So I think that the details of this are they compare the embedded optimal regime to some baseline standard of care or something like this. I forget exactly what regimes they're comparing, but in any case, this is the sort of standard that they're comparing against. And then we look at cases where the limiting variance of the plug-in estimator of the value is known and when it has to be estimated from pilot data. All right, so these are the samples, the simulation results. We can go through this together because I am not all that familiar with these either. But typically, in the correctly specified case for the parametric approach, we do achieve the nominal power or close to it, and we do achieve the probability of being within the desired epsilon that we wanted as well, at the expense of somewhat higher sample sizes than we would have had had we just powered for the difference between the embedded regime and the baseline that I mentioned. I'm not sure what's going on here, frankly. I'm sure there's some explanation for this, but I just noticed it. But otherwise, these sample sizes are higher than this. Okay, and in the misspecified case, looks like we have some robustness over here, achieving the nominal power in most cases. Our probability of being optimal, though, it is hurt in a few places. And the estimated sample sizes are again, considerably larger. I guess, I say considerably, but I don't have a good sense for what counts as a much larger sample size now that I think about it. So when they say estimated, so when they say pilot study, they assume that this limiting variance is estimated from some existing data set. So no, this is all prior to the study starting. Okay, so that's it for the parametric sample size formula. And then this is the wording is different, but this is also the correctly specified and incorrectly specified case. Our power is pretty close to the nominal level when there is an effect, but we are not getting as close to the probability of being near optimal as we were before when we made parametric assumptions and the model was correct. However, we still do pretty well in the misspecified case. So, all right. We can go back through these if anyone has any questions on that. All right, so altogether, we have, it is possible to power studies for the estimation of a high quality regime that is not, to get procedures that are not excessively conservative, sample sizes that don't look prohibitively large, attain nominal frequentist operating characteristics, and with a range of assumptions on the generative model. We do require, at least in the case with few assumptions, that there be some historical data to oversample from. And Eric says that these are the first steps, but there are many interesting open problems. So you are welcome to contact him at that address. You can contact me too, but I don't know anything about this. So. I will try my best to field questions. Delta is the true effect size. Here? Oh, so this is the difference in means between the optimal regime and best fixed non-adaptive regime and eta units. So it is a difference. So this is what you were confused about? Sure, yes. I will direct you to this slide. I don't think so. So as far as I know, that this is original to these authors. So yeah. Uh-huh. Mm-hmm. Right. So, as far as I understand, that would just be treated as still as the observed as the outcome of interest, even if there's a delay between the stage 2 treatment and the measurement of the outcome of interest. So I don't know if people have modeled this in different ways. Maybe someone else knows more about that than me. So I think that was addressing the delayed effect of treatment 1 on the outcome of interest, but not if there's a long time between treatment 2 and the outcome, which is, I think, Lauren's question. No. Right. I mean, you're still free to talk about the conditional mean of the outcome, because the signal may just be really weak if there's a long delay or something. So are you thinking that we're actually considering patients in sequence? Because I think that patients are treated as a batch in these trials. Yeah. So I think that gets around the concern you have. Yeah. Mm-hmm. Yeah.